the Biology and Space Exploration video series. At NASA, our goal is to explore and utilize space to help America advance science and technology. In these videos, we'll investigate the effects of the space environment on life and see how space research can benefit us right here on Earth.
And we have a go for main engine start. 5, 4, 3, 2, 1.
Today, it is a commonly held scientific belief that life, including intelligent life, exists on other planets orbiting other stars. The scientific community has begun an attempt to find ways to substantiate this belief. The purpose of SETI, or the search for extraterrestrial intelligence, is to detect evidence of such intelligent life in our Milky Way galaxy. One of the earliest documented ideas about the existence of extraterrestrial intelligence dates back to over 2,000 years. In the 4th century BC, the Greek philosopher Metrodorus said, "To consider the earth as the only populated world in infinite space is as absurd as to assert that in an entire field of millet only one grain will grow." Despite such an early claim to the existence of life elsewhere, there were very few proponents of the existence of extraterrestrial life until the 15th and 16th century, when Copernicus and Galileo challenged the Ptolemaic view of Earth as being the center of the universe. In 1959, a new field of science called exobiology emerged. Exobiologists study, among other things, the origin and evolution of life. In studying the chemical origin of life, exobiologists theorized that all living things originated from inanimate matter. They also discovered a large number of carbon-based interstellar molecules and suggested that life forms, based on a molecular structure similar to ours, may have evolved on planets revolving around other stars. These theories on the origin of life fueled the argument for the existence of extraterrestrial life forms. If the same raw material leading to life on Earth exists on other planets, it seems logical that life can also evolve on these planets given the appropriate conditions.
Everything we have learned in our study of the cosmos, of the origins of life, of the evolution of life, have suggested that the processes which caused us to be here are completely normal processes in the evolution of stars, planets, and eventually biology. No freak circumstances were required for us to be here with our high technology, and therefore the steps which led to our existence should have occurred in many, many places.
With the realization that the origin and early evolution of life can be universal, people started speculating that there may be other forms of intelligent life throughout the galaxy. The new challenge was to find ways to detect these life forms. Given our present level of technology, detection of other life forms is extremely difficult, and traveling to other stars is presently impossible. Even if we were able to develop the technology to travel near the speed of light, it would take at least a few decades to reach stars that exist many light years away. Such a long voyage would require so much energy and supplies that it would be difficult to accomplish. Instead of relying on future technology, we try to work with a technology that we already have. One such technology gives us the ability to detect electromagnetic signals at great distances from our planet. In 1959, Cocconi and Morrison published a paper proposing the use of radio telescopes that would search frequencies near the hydrogen line of 1420 megahertz to detect extraterrestrial civilizations. Following this publication, an astronomer named Frank Drake independently carried out the first search for extraterrestrial intelligent life in 1960 by aiming a radio telescope at 2 nearby stars. This technique of searching for signs of extraterrestrial life set the foundation for the SETI program. In 1971, NASA first showed interest in the search for intelligent extraterrestrial life when it published Project Cyclops, a design study of a system for detecting extraterrestrial intelligent life, co-authored by Barney Oliver and John Billingham. Over the next 20 years, NASA developed its own SETI program, which became known as the NASA High Resolution Microwave Survey. Then, in late 1993, the SETI Institute, a privately funded nonprofit research organization in Mountain View, California, undertook the search, now called Project Phoenix. Although there are additional SETI programs in several countries, Project Phoenix is by far the largest search now being undertaken.
One of these days, we may actually detect a signal from an extraterrestrial civilization. All those with interests in life in space are going to be very fascinated with the discovery of what their chemistry is, what their biology, what their evolutionary processes are, and of course what their intelligent species is actually like. But it's not just an interest from the point of view of the scientist. Whatever walk of life you come from, be it from the arts or philosophy or history, religion, they will have their own variety and version. It's going to be different from ours. So it's going to be just a fascinating discovery.
Researchers at the SETI Institute believe that if civilizations are technologically advanced, they will emit radio waves of frequencies similar to those used on Earth. SETI scientists aim to detect these radio waves using large radio telescopes. However, the question of probability arises. Will chance be in their favor? And will they be able to detect anything in such a vast galaxy? One way of estimating the distribution of technological societies on other planets is to use the Drake equation. This equation, presented by Frank Drake in 1961, is used to calculate the number of detectable civilizations in our galaxy. The equation states that N is equal to the product of R, Fp, Ne, Fl, Fi, Fc, and L, where N is the number of civilizations in our galaxy whose radio emissions are detectable. Although values for the variables are probabilistic, SETI researchers have made estimates of these values based on careful evaluation of available facts. The first variable, R, is the rate of star formation in the galaxy per year. The value used for R is 20 per year, which is known to be reasonably accurate. The value Fp refers to the fraction of suitable stars that have planetary systems. Not all stars are suitable to bear planets. Stars range in size from the large O stars to the much smaller M stars that are barely large enough to have nuclear reactions. M stars do not radiate enough energy, and O stars have so much energy that they destroy themselves before the evolutionary process of life on planets has time to occur. The ideal stars are the F, G, and K stars that have masses close to that of our Sun and that can irradiate planets to temperatures that are suitable for life. However, not all F, G, and K stars necessarily have stable planetary orbits, since many stars belong to binary or multiple star systems. SETI scientists estimate that about 50% of the F, G, and K stars will be good suns and have planets with stable orbits. Since F, G, and K stars make up about 20% of all stars, then the value of Fp turns out to be 0.2 times 0.5, which gives us an Fp value of 0.1. The next variable, Ne, refers to the average number of planets within these stable planetary systems that are ecologically suitable for life. The presence of liquid water on a planet is often considered a good criterion for whether or not the planet will be suitable for life. In our solar system, there is a region known as the circumstellar habitable zone. It is believed that if a rocky planet is in this region, it will be able to sustain life. Notice that Earth is in this region and that Mars is also on the border of this region and may have sustained life in the past. Due to the lack of astronomical evidence, SETI scientists base their value of Ne on our own solar system that has at least one life-sustaining planet. It is therefore assumed that the average number of Earth-like planets per good sun is equal to 1. Computer simulations of planetary systems produce the same values. The term FL is the fraction of these Earth-like planets on which life begins. Presently, most exobiologists believe that if a good sun and a good Earth have evolved, then life will begin, so FL is chosen to equal 1. Fi refers to the fraction of these planets on which life actually gives rise to intelligence. The type of intelligence that concerns us is the cognitive type of intelligence possessed by human beings, and some estimate this value to be 0.05. Fc is equal to the fraction of such planets in which the intelligent life evolves to an advanced communicative technology. Most people argue that the probability that communicative technologies will arise from intelligent life is very high. Therefore, they choose Fc to be equal to 1. L, the final variable in the Drake equation, refers to the average longevity of civilizations in the galaxy. Its value is the most subjective in the equation, and hence the most difficult to predict. Some choose it to be 10 to the 6th, while others, who are more skeptical, choose much lower numbers. It is now 1996, and we have been in the category of an advanced communicative civilization for just over 60 years, and some argue that we will not survive for much longer. Therefore, we sometimes leave the value for L blank, and then see how N varies when we substitute different values for L. Based on the resulting value of N, we can calculate the mean distance between communicative civilizations in the Milky Way galaxy. Using the values previously given, our calculation for the value of N is equal to 0.1 L. The following table demonstrates the different N values and mean distances we get when we select a range of L values. For example, if we chose the mean longevity of a civilization to be 1,000,000 years, then we can calculate that there are 100,000 civilizations in our galaxy and that the mean distance between civilizations is 464 light years. This number also tells us that it will take 464 years for the signal to reach the Earth. Notice from this table that any civilizations that SETI actually detects will be much older than we are. We have only been able to send out strong radio signals for a few decades, so we are in our infancy. Viewed against the geological timescale, we are therefore the youngest technological civilization in the galaxy.
Any society that we discover will be much older than we are, perhaps 1,000,000 years, perhaps 10 million. So we'll be able to learn a lot from them. They will be probably more advanced, and they will have passed through the same early stages that we're going through now, and they will have emerged a long time after that with a stable and long-lived society. Perhaps this gives us some hope and comfort for our own progress towards such stability and longevity in our own society.
Due to the low probability of signal detection, SETI scientists and engineers have had to devise a technique of maximizing detection. This is done by optimizing targets, maximizing sensitivity, and optimizing signal detection. To optimize targets, SETI selects particular stars that fit certain criteria. These stars must be nearby, older than 3 billion years, and mostly single FG or K stars. Nearby stars are targeted because their signal will be stronger and take less time to reach the Earth. Stars older than 3 billion years are used because, based on our own planet, it might take at least 3 billion years for civilizations with communicative technology to evolve after the formation of a star. The targeting of single FG or K stars, as explained earlier, is based on their likelihood of sustaining planetary systems. In order to maximize sensitivity, SETI researchers use large radio telescopes, low-temperature receivers, long observation times, the microwave region of the spectrum, and narrow band detection, which allows one to distinguish technologically generated signals from the broader band emissions of natural astrophysical processes. The larger the radio telescope, the greater the probability of picking up a signal. Presently, the largest antenna used is located in Arecibo, Puerto Rico. The terrestrial microwave region is significant.
There is a preferred region in the electromagnetic spectrum, we believe, that minimizes the energy required to make contact, and that is in the microwave region. And the reason for that is that the noise that would interfere with our transmissions, or theirs, is lowest there.
This figure illustrates a measure of the temperature depicted as noise at different frequencies of the electromagnetic spectrum. The purpose is to make sure that the search is at a frequency where there is low noise, so we can distinguish a signal from the background. In the lower frequency end of the EM spectrum, there is a high degree of noise due to radiation from the galaxy. In the higher frequency end of the spectrum, there is also a high amount of noise due to the presence of oxygen and water in the atmosphere. The best region turns out to be that part of the spectrum between 1 and 10 gigahertz. This region is called the microwave window. In order to optimize signal detection, SETI investigators use all polarizations, multi-channel spectrum analyzers, Doppler drift detection, continuous wave detection, pulse detection, automated analysis, radio frequency interference or RFI rejection, follow-up detection, and confirmation by one or more separate observatories elsewhere. Doppler drifts are apparent changes in frequency due to the movement of the source towards or away from the observer. They need to be taken into account due to the rotation of planets. Therefore, if electromagnetic waves were emitted from a source on another planet, the frequencies would appear higher when the source was moving towards the Earth and lower when moving away. SETI solves this problem by looking for a very large number of different frequency drifts between +1 Hz and -1 Hz. Follow-up detection devices and radio frequency interference rejection strategies are very important for the avoidance of misinterpreting signals. The devices that analyze the spectrum look for peaks above the background signal as an indication of a technology-generated signal. However, even though SETI systems have detected a number of such signals, subsequent analyses have shown that these signals were all generated on Earth. SETI observers also attempt to avoid these interfering signals by selecting an isolated location for the receiver. An ideal location is on the far side of the Moon. Since this region always faces away from the Earth, Earth-generated signals would not reach the detectors. The overall prototype of the Project Phoenix system is as follows. The antenna picks up the incoming waves and sends the signal to the radio frequency subsystem. The radio frequency subsystem sends the input to the multi-channel spectrum analyzer, or MCSA, that has 28 million separate individual channels. Its output is then sent to the signal detection subsystem that looks at all channels to see if there is a strong signal. Strong signals, which appear on the monitor as spikes, are then sent to the data collection archive subsystem, which stores the information. On receiving a signal, the SETI scientists are alerted and follow procedures needed to verify the signal. Until present times, all of the strong signals detected by Project Phoenix have come from the Earth. However, let's imagine that one of the signals does appear to be real. In such a situation, the SETI scientist will then contact other observatories with radio telescopes and give them all the signal characteristics to find out if they can also detect this signal. After weeks of verification, much effort might have to be put into interpreting the signal. There is always the possibility that these signals could carry a message. A civilization less than 30 light years away could have detected one of our strong radio waves and responded. Signals from civilizations further away could also carry messages, but they might not.
One of the questions that we're often asked is, what do you do if you actually detect a signal? And this is more complicated than it looks at first glance. Most SETI scientists take the position that any signal we detect is automatically the property, as it were, of all humankind. And therefore that we should instantly tell everyone and invite everyone to study the signal and take it from there.
Evidence for the existence of extraterrestrial intelligent life will have important consequences. Because of the profound implications of initiating two-way communication with an advanced civilization, we must consider whether or not to respond and how to respond. Because we cannot predict the nature of the signal, it is difficult to determine a response until after a signal is received. The response that we transmit will depend on a number of factors, including the type of signal and the content of any message. However, it will also largely depend on our own reaction to the knowledge that extraterrestrial intelligent life really exists. All of these breakthroughs have been facilitated by the curiosity and hard work of scientists engaged in the study of space. The success of NASA depends on our ability to attract talented scientists and promising researchers to participate in this effort.